Hello, in this section I'm going to talk about L'Hopital's rule, but we really call it indeterminate limits. Okay, so we have that, let's say that you have a limit and we're saying that if we take x approaches a and we have f of x, and then we have that this is going to be g of x, but of course, well, what we have to have is that the denominator does not equal to 0, but here's what happens. Let's say that you get that f of x tends to 0 and g of x tends to 0. So in this case, we have that this is what we call indeterminate form. Okay, now you did see some examples before. So like one of the most classic ones is like if you have the limit as x approaches 4 for the square root of x minus, let's say, 2, and this is all divided by x minus 4. Now, you have that, yes, if you do plug in 4, you do get 0 over 0. Now, previously I might have said that we just need to rewrite this so that you can basically get that the limit value is actually equal to, let's see, it's actually equal to 4. Okay, now the question though is, well, how can we do this using our L'Hopital's rule? So what L'Hopital's rule says is that essentially you have that if f prime of x divided by g prime of x tends to, let's say, L, then this means that f of x divided by g of x also tends to L. So the question though still remains is like, okay, well, how did we get that? So, and of course this is provided that g of x is not equal to 0. Um, Now, the way in which that we can look at this is that, for instance, now keep in mind that L'Hopital's rule applies for multiple situations, like if f of x, or if x is approaching a, or x is approaching a from the left, or if it's approaching a from the right. But furthermore, it also goes with like if it's approaching infinity or if it's approaching negative infinity. So L'Hopital's rule actually has several different cases. So if we take the limit as x approaches, let's say, just a, and we have f of x is equal to, or divided by g of x. Now, I know that basically I can rewrite this as the limit as x approaches a for, let's say that this is going to be rewritten as f of a plus f prime of x times x minus a, and then all of this is divided by, all of this is divided by g of a plus, g prime of x multiplied by x minus a. Now, what you'll notice is that basically this cancels out. Why? Because it's 0. And then this cancels out. Why? Because it's 0. But then you're left with this, and that cancels out too, that factor. So what ends up happening is you end up with reduction of the limit as x approaches a for f prime of x divided by g prime of x. Now, of course, what that's telling you is that if x approaches a and it's still 0 over 0, you just apply it again. So in this case, we'll just say that this equals to f prime of a divided by g prime of a. Now, typically you might actually say that, well, this equals to just say some value L. So all that we need to do is just to apply L'Hopital's rule, which means just take the derivative of the numerator and denominator as many times as possible. So if that's the case, then that means that with the example that I gave, like the square root of x minus 2 divided by x minus 4, you just have to take the derivative. Now, normally we just like to say that, I think my answer might be actually wrong. Let me see. Yes, my answer back over at the very beginning is actually incorrect. But we'll see. It's actually 1/4. Yeah, this should be 1/4. But we'll actually see that in a second. So I indicate that I usually take the derivative by putting like a little star, and that way we know that we applied L'Hopital's rule. So we have the limit as x approaches 4. Now here you take the derivative of x minus 4, which is just 1. You take the derivative of root x minus 2, which is 1 divided by 2 root x. Now here, notice that if you plug in 4 now, you get 1 over 2 root 4 divided by 1, but that's equal to 1/4. Okay, now in this case, that means that we can apply L'Hopital's rule as needed, for instance. So let's just try one more example. So let's say that we want to find the limit as x approaches 0 for, let's say, sine of x divided by x. Well, this is also a classic problem because if I plug in 0, I get 0 over 0, which means that it is actually in our indeterminate form. So what that means is that we can actually just go ahead and take the derivative on top and bottom. So we have the limit as x approaches 0 of cosine of x divided by 1. But if you do x to 0, that's going to be cosine of 0, which is just 1, over 1, which is actually just 1. So the limit is actually just 1. And that's it. Now, I would recommend that you go ahead and you try the limit as x approaches 0. Actually, it's, yeah, 0 for e to the x minus 1 divided by x, and then see what you get. Now, we do have that there are more different forms of indeterminants. You have that another form could be infinity over infinity. Another could be like infinity times 0. But another form could be like if you have 1 to the infinity. Okay, so that doesn't really help us, for instance. And then you also have like zeros to the zeros and whatnot, but these are the most common ones to look at. Okay, so yeah, we do have the 0 over 0, like 0. I guess we'll put it, 0 to the 0. The other form of which that we might have is such as like if we have 0 but to the infinity. Let's say that you go ahead and you try another one, such as like if we're going to try the limit as x approaches infinity for natural log of x divided by x. Now if we go ahead and we see this, we see that it approaches infinity over infinity. So what that means is that we just have to take the derivative on top and bottom. So we have the limit as x approaches infinity, and then we have 1 over x, and then that's divided by 1. But in this case, this tells us that as x approaches infinity, that's going to go to 0 over 1, which is actually just 0. So the limit is 0. Now, I would say that, like if we go ahead and we look at, let's say like another one, like if we have that we want to find the limit as x approaches infinity for x sine of 1 over x, well, notice that if you go ahead and you try to go to infinity, that's going to go infinity times 0. So in this case, like what has to happen is that you have to rewrite it. You have to rewrite it in a way that we can put it back into an original indeterminate form. So we can say that, for instance, that you can rewrite it as sine of 1 over x divided by 1 over x. And now, if you go ahead and you notice that if you take x to infinity, this becomes 0 over 0, which basically means that we're in the original indeterminate form, which means that we can then apply L'Hopital's rule. So we apply L'Hopital's rule by going ahead and taking the derivative on top and bottom, of which this is going to be cosine of 1 over x multiplied by negative 1 over x squared divided by negative 1 over x squared. But you'll notice that basically the 2 cancels out. So now we will get cosine of 1 over x, just cosine of 1 over x. So we have the limit as x approaches infinity of cosine of 1 over x, which if we take x to infinity, that's just going to be cosine of 0, which actually is just 1. So the answer is 1. Now, another classic example. Another classic example is something like if we have like 1 to the infinity. Okay, now if you recall that when you were taking the derivative of the exponential function, most likely you had the situation of, let's see, well, how about this? Yeah, so in deriving, say for example, the letter E, or the transcendental number E, we have that we would look at something like this. Like if we have the limit as x approaches infinity for 1 plus 1 over x raised to the x, this actually goes to the letter e, so like e to the 1. Now, you can try using L'Hopital's rule. So, for instance, let's say that we go ahead and we try a different one though. We have that we want to find the limit as x approaches infinity for 1 plus 2 over x raised to the x. So let's say that we go ahead and we try to find this. So notice that this is still just 1 to the infinity, meaning that we can go ahead and find using L'Hopital's rule. But the thing though is that we have to do more. So this is where it gets a little interesting. Well, let's say that we go ahead and we let y equal to the limit as x approaches infinity for 1 plus 2 over x raised to the x. So in this case, we have that we can take the natural log. So we have natural log of y equals to, now here's where it gets a little interesting. Because I took the natural log, and because of the fact that the limit operator can be interchanged, like it can be brought in or out and so on, well, this means that we're going to have the limit as x approaches infinity for natural log of 1 plus 2 over x divided, or raised to the x, sorry. Now, notice that the x actually does count. It comes out. So we have x approaches infinity, and this is going to be x multiplied by natural log of 1 plus 2 over x. Now, note that basically when we rewrote it, now we have that this is infinity. So now that we have that this is infinity times 0. Okay, that's kind of interesting because now it's infinity times 0. So what that means is that we have to rewrite it. So we have the limit as x approaches infinity of the natural log of 1 plus 2 over x, all divided by 1 over x. Now notice now that this is still going to give us just 0 over 0 because you have that's ln of 1, and that's just going to 0. So that's still indeterminate form. So now we can go ahead and apply finally the derivative. So all of this was just rewriting it. So we have the limit as x approaches infinity of, well, okay, do it like this. We have 1 divided by 1 plus 2 over x multiplied by negative 2 over x squared, and then we have negative 1 over x squared. Now, notice this. The negative 1 over x squared cancels out with the negative 2 over x squared, but it's just going to be 2. So this simplifies to the limit as x approaches infinity for 2 divided by 1 plus 2 over x. But notice that if you take the limit as x approaches infinity, that this is just going to be 2 divided by 1 plus 0, which in this case is just 2. So we have that the limit value is just equal to 2. But be careful. We took the natural log. So what this means is that the natural log of y equals to 2, which essentially means that that y is equal to e to the 2. So what that means is that the answer is actually e squared. So we have that this is going to be equal to that the limit as x approaches infinity for 1 plus 2 over x raised to the x is actually just equal to e to the 2. Now, interestingly enough, you can actually generalize this, but it's really best that you really don't, because it would have to be specific as to the format, and it's a lot better just to do it from scratch, if anything. Um, so with that, like for instance, let's say that you had the limit as x approaches infinity for x plus 1 divided by x minus 1, and then let's say that it was raised to the negative x. Well, in this case, you have that this is going to minus infinity, but this is like it's going to 1, and then you have minus infinity. So the question then becomes like, what would you do? So that's what I mean by it's probably just best not to generalize it and then just try to work it out. But, there is a trick to this. You can actually just rewrite it in the following manner, where you just say that this is really just x plus 1 divided by x minus 1, and that's raised to the x. So you could probably just concentrate on just this one, and then note that it's raised to the negative 1. So that means that you could probably just disregard the negative 1 for a minute and then just figure out what this is on its own. Yeah. Okay. Now, I do recommend that you do look at some other forms of indeterminate. There is another form that is practiced like infinity minus infinity, but usually it means that you just have to rewrite the equation or the expression for that matter. But do go ahead and try to look at those because that's a little bit interesting because it's like saying which one comes first or which one is larger in this sense. So that way you can get the whole limit value.